Hello everyone. Today our topic of discussion is compact model for low FFT mass channel common double gate MOSFET. Uh, this research of ours got published in IEEE transactions on electron devices very recently. So going directly into our topic of discussion. So before going into the transport modeling, how I model the transport equation, I would like to briefly recapitulate the surface potential model published in our earlier research. Uh, it was a purely physical surface potential equation for LDOS material common double gate MOSFETs. It's given in equation 32 in this in our previous research. It is purely portable. It is very portable in nature. You just have to play with this nmax parameter in the surface potential equation. You just change this nmax parameter. Nmax is the maximum number of subbands, which is in our case 3. So you make it 1, make it 2, make it 3 the based on need of the engineer or the designer. And mi dashed, mi double dashed, these are the parameters for these are the bias independent parameters for perturbation. uh, Eg is the band gap. So from this equation we solve for phi m, and through a linear relationship given in our paper we obtain front and back surface potential. For for viewers, for ease of the viewers, I have provided this relationship. QV is equal to minus EF. QV is V is nothing but the channel potential, and EF is the Fermi level. So this is how I model the transport. In conventional silicon MOSFET, semi-classical drift diffusion is used, which is given by the above relationship. Here UT comes from Einstein's relationship. Phi is the electrostatic potential, and Q in is the inversion charge. But in case of low density of state material MOSFETs, it changes to quantum drift diffusion, where this electrostatic potential changes to energy eigenvalues, which is obtained through adding Bohm potential, which we can which one can read in detail in this paper. And this di is no more uh, kt by q. Di by mu is no more kt by q due to the change in material, and it takes a bias dependent form, so we cannot directly solve this equation. And this QACI is the charge density along the channel. It's given by this relationship. It changes along the channel along with the eigenvalues, which all are function of y, or the along the channel length. What happens in quantum drift diffusion? The quantum confinement is in our case in x direction, and transport is in y. So quantum drift diffusion combines both of this, and it carries the essence of quantum confinement in transport. uh, the X confinement affects the drift and diffusion of carrier. So this is called quantum drift diffusion. It can be read in detail in this below mentioned paper. So going directly into the challenges what we face during the modeling. The In case of conventional silicon, the Fermi level is uniform. The Fermi level does not change through subbands. But in case of quantum drift diffusion or low density of state material, uh, due to strong transverse confinement, all the subbands, they have their own distinct quasi-Fermi levels. The carriers, they are in local thermal equilibrium in each subband. So we have different quasi Fermi levels for each subband. So for our three um, distinct energy subbands eigenstates, we have three distinct quasi Fermi levels. They all thermalize in source and drain. In the drain region, as we can see, I have provided 1.5 VDS. So it all of the quasi Fermi levels, they thermalized at 1.5 electron volt. And for clarity of the for sake of clarity, I have provided this value of quasi Fermi level at source and drain, which are given by 0 and q minus q VDS, which we will be using which we have used in our modeling. Let's discuss the shortcomings of some previous works which are marked shortcomings. Like quantum confinement was earlier captured only in electrostatics but not in transport. Uh, this was a big mistake uh, in previous works. It actually incorporated same quasi-Fermi level for all subbands, which is actually not true, as we have described in previous slide, due to strong transverse confinement in our case. Heavy use of interpolating functions and empirical parameters that affected the physicality of the model. Uh, that's why that's why ultimately the equations were not uh, the models were not completely trustworthy for all regions. And some of the works, they led to highly complex mathematical models which are ultimately not useful for circuital implementations. So in our case, we implemented quantum drift diffusion along with a novel charge linearization scheme that gave us very simple transport model that we have discussed in detail in our paper, and we will briefly describe it in this slide. This is the charge linearization. As we can see in these two plots are directly taken from these two plots are from TCAT data. As we can see, the subband quasi-Fermi levels and subband charge densities, they share a linear relationship with subband energies. So for an extensive range of device parameters and VGS and VDS, they share the same linear relationship. So we exploit this linear relationship with in our model. We just change the variable from quasi Fermi level to subband eigenvalue, and we ultimately obtain a very nice compact quadratic relationship of I current versus current and source and drain charge densities that one can see in detail in our paper, along and also the how we derived the whole relationship. So this is the overall roadmap of this work. First, we obtain the solution of surface potential at source and drain uh, using the surface potential equation that I have described in the second slide. And then we find the source and drain charge densities, and we use all this to the novel charge linearization scheme to solve the quantum drift diffusion current transport. We obtain a very nice current equation that is quadratic in nature, that gives very good uh, very good matching with TCAT data. And ultimately we model the terminal charges using conventional techniques and Watt-Dutton charge partition. So this is the overall summary. It's a purely physical current and terminal charge model for um, low effective mass channel material common double gate MOSFETs. We derived it under quantum drift diffusion. It's absolutely portable. One can change number of subbands. One can change the order of perturbation, and obtain a physical relation, very physical and completely analytical relationship without ever using a single fitting uh, or or any kind of forced uh, forced mathematics. So, and it covers a very wide range of semiconductor thickness and other other device parameters, along with a considerable range of gate to source voltage and drain to source voltage. And finally, the biggest advantage is it allows us it has first time given the opportunity to extend the quantum diffusion formalism to circuit simulation, which has so far been limited to device simulation. We can actually design circuits using uh, this model. So this is a very brief flow chart of what we achieved and what can be the future work. Uh, so thanks viewers for the kind attention.